Hello and welcome everybody to the next phase of our discussions on FEEP and WAM software, and we have completed the mathematical jugglery, and now we will be talking about the actual theoretical aspects of the shell. So we'll be starting with the kinematics first, and then we will move on to balance laws, energy equation, weak formulation, linearization, and FEM discretization. So many things to talk about. In this video, I am planning to cover kinematics and balance laws till section 4 of the part 1 of this series of papers. So let us start. So the basic assumption in the kinematics is that of an inextensible one-director coherent surface. Other than this, there is no assumption, and by making this assumption, what they say is that the director vectors will remain as unit vectors. They need not be normal, they can have any arbitrary angle to the surface, but they will remain as unit vectors. They will not be extensible, and there will be a single director. That means if we look at the WAM description, we have three warping components, all three along three different directions. If it is in capital BI system, so three along three mutually perpendicular directions, but here we have a single director, and it need not be in any particular coordinate directions, it can be an arbitrary direction, so it will have an effect of all three warping directions embedded into one director vector, and it is inextensible. That is really a constraint because we may have extensions of the director. So in part 4 we will see this limitation is also removed by employing further extension of the SO3 and S square relationship. So that we will see, but for now we will assume that director vectors is inextensible. So basically we have two maps phi and t to describe any general configuration of the shell. So phi maps the points which are lying on the mid surface of the shell. So it is from A to R3. A is basically denoting the Euclidean space or plane of the Euclidean frame of reference, and it has the coordinates zeta1 and zeta2 to describe any vector on this surface. It is a rectilinear plane. And t vector, which is denoting the director vector, it can have any orientation on the entire unit sphere. So it also takes its input from zeta1 and zeta2 from the Euclidean plane and maps it to a unit sphere S square. So these two are the maps which are used to describe any configuration of the shell. So it can be written as x, any general point on the shell body can be written as x is equal to phi plus zeta t, where zeta belongs to h minus to h plus. And if we talk about the reference configuration, which is denoted by this stylized b, this also can be written as x naught is equal to phi naught plus zeta t naught. So this is how it can be written as. And if we talk about the deformation, it is a mapping from phi naught to phi, or in other words it can be written as phi of phi naught inverse. Now if we talk about the deformation gradient, the deformation gradient can be written as grad phi of grad phi naught inverse. This can be understood better in this picture. So phi naught takes the input from here and takes it to the undeformed shell, and phi takes input from here, same place, and takes it to the deformed shell. So if we want to write a mapping from here to here, So what we have taken here, we have to bring it back, that means phi naught inverse, and that we have to take through phi. So phi of phi naught inverse will take us to the deform from the undeformed. And similarly in the deformation gradient, that is how we write grad phi of grad phi naught inverse is the deformation gradient. So once we have the expression of tangent map, we can write covariant and contravariant vectors, and these will be used to write the expressions of stress resultants later on, as we will see. Moving ahead, these are the expressions of Jacobian of the deformation gradient and other contravariant basis vectors like G superscript 3. And next we have two important frames of reference on the mid surface. So if we consider G, what we have defined over here as covariant vectors, if we take that G on the mid surface alone, that means phi comma alpha, and call it A alpha, that denotes the convected basis or surface. It forms a surface convected frame. So A alpha, the two vectors on the surface of the shell along the coordinate lines, and a perpendicular vector A3 is equal to G3 is equal to T. So these three form a convected frame of reference, and another frame of reference is director orthogonal frame. About this we talked a little bit in the previous video when we saw in part 2 of the paper series that these three are mutually orthogonal and all three are unit vectors, and they are coming from this exponential map only, and this is how they are related. So this is yet another frame of reference which is called as director orthogonal frame, and this will be mainly used in the mixed formulation which is developed in part 2 of the series of papers, and the displacement based formulation is developed using this surface convected frame of reference. So in this picture we can see the slight differences which are there between these two frames of references, and we'll be using both in the further developments of the theory. Next, our target now is to write the conservation equations, conservation of linear momentum, angular momentum, and for that we need to have first the expressions of the inertia terms which are like dp by dt, rate of change of linear momentum or rate of change of angular momentum in terms of angular velocities or linear velocities. So first we will be writing that, and then we will look for how we can write the expressions of internal stresses, which is actually 3D stress, and we will be integrating it over the thickness direction to get the stress resultants. So these stress resultants will actually cause the inertia terms. So that is how it is related in the momentum equations and angular momentum equations. So first we will look at how to write linear momentum, angular momentum and director momentum, all three. So in order to do that, we'll first look at the inertia terms. So we have T dot coming in. So how to write T dot, that is in terms of the angular velocity. So this we have already seen in the corollary 2.2 where we saw that omega hat lambda was lying in the tangent space of SE square at lambda, and how that is related to tangent space of S square at t when we take its cross product with t. So this is essentially what is being done here by taking this w hat t, or in other words it is written as w cross t. Okay, so we can note from here all these three, w hat lambda and lambda capital W hat and lambda dot, all these three are actually belonging to the tangent space of SE square at lambda. And also we can note down this relationship between lambda dot and W hat. So this is how we write the angular velocity, and this we will be using to write down the expressions of the linear and angular momentum. Here is a small discussion about the density and inertia terms and how they are averaged out over the thickness direction through the integration through thickness, and then they are used to write the resultant linear angular momentum and director momentum. So we have a time differentiation of phi map, and this is all what we get. So linear momentum is defined as this rho phi dot j d xi integrated over thickness 1 upon j to average it out, and what we get is this as the linear momentum. And here, since we have t dot terms, so we get this relationship. So is some more intermediate steps are there which I have provided here, can be seen to check the jump from here to here. Okay, so next we will look at the local balance laws. So we have already written the expressions of the inertia terms, and now we are going to write the internal force terms in terms of the stress resultants. So from the 3D theory of elasticity, we have the 3D stress, Cauchy stress, Piola-Kirchhoff stress, and both of these we are going to integrate them over the thickness direction and get the expressions of stress resultants, and in terms of those we are going to write our momentum equations. So here is the process to follow. We have this expression from the continuum mechanics relating the differential amounts of area as it transforms under a deformation gradient and become from d capital A to d small a. So d small a is written as j inverse SI DAS, and that is actually being used here to write this expression, to bring this expression of the force from the current configuration or any general configuration of the shell to the Euclidean space. So this is J Jacobian, Jacobian of deformation gradient, times F inverse transpose, which gives this term, times NDS. NDS is nothing but this dA. So this is what it is written over here, and the left side what we have is d small a, which is n hat ds, which is in the current configuration. So this we use, this is in the current configuration, and this we bring in and multiply it with sigma, which is also in the current configuration, and we get sigma g1 j d xi integrated over thickness, and this we multiply with x minus phi, which is along the thickness direction in the current configuration, and multiply that with the force due to sigma, and we get what is the torque. So this R1 basically gives us n alpha, and T1 gives us m alpha. Alpha is 1 or 2. So we get n1 n2 and m1 m2. Both of these are in the current configuration. So I have drawn a small picture to show the directions of all of these. So we have n1, and this is also n1 in the outward direction. This is a stress resultant force, and n2 and n2 here. So both n2 are acting over here, and m1 is like this here, and on this face it is like here, and m2 is here, and here it is, because this moment arm is being multiplied with n2 to get this m2. So it is in this direction. So that is how it is. And if somebody wants to refresh the basics of Piola-Kirchhoff and Cauchy stress, I have written some important relationships over here, drawn something in the picture also. So I hope this would be helpful. So we'll move ahead and will not discuss anything much over here, and we'll look at the expression of across the thickness stress resultant, which is also coming over here in a similar way. And all those expressions which we have written for sigma can also be written for first Piola-Kirchhoff stress, and this is how it is. Very easy derivations. Whatever few steps are missing, I have just written down them over here and verified everything coming out to be correct. Next we have the expression of m alpha. Here we have to see that there are some derivation steps involved over here. See, we have this as t cross something. So whatever we have, this, let us call it as m tilde alpha, it is going to be perpendicular to t. Okay, this m alpha is going to be perpendicular to t. And if we write this m tilde alpha as m parallel tilde alpha plus m perpendicular tilde alpha t, so this component, the first one, will not be contributing anything to this final m alpha, because this will become 0. So it is only this component which will be contributing. So we can write it as t cross m tilde alpha perpendicular t, and this we are calling it as t cross m bar alpha, which is mentioned over here. So m bar alpha can be written as m tilde alpha and subtract from that the component which is parallel to t. So we get this m bar alpha, and this is the effective moment which is contributing in the moment equation. So we have written the expressions of stress resultants as n alpha, moment resultants as m alpha, and director stress resultant across the thickness stress resultant as L. And now all these three will be used to write the momentum equation. So the momentum equations are developed in the appendix. So we have already checked and these are correct. Very easy derivation. So these are used, momentum balance equations of the three-dimensional theory are used to derive the resultant local form of momentum balance equations, which take this form. So please note that here we have m alpha coming in, not m tilde alpha, which is this m alpha is coming over here, not this m tilde alpha. And later on, after some further processing, this will be converted to m tilde alpha. And this is not the final form of momentum equations which will be used in the modeling. This will be modified further, and then that modified form will be used in the modeling of the shell theory. Here an important note is mentioned that many authors have reached to these equations and they proceeded directly to convert them in component equations in the Gauss frame, and that made this complications to arise in terms of Christoffel symbols and Riemannian connection of the mid surface. So in this paper they have avoided that route and they have kept the form of these equations in terms of the vector equations only, and that way this Riemannian connection of the mid surface does not enter explicitly in the formulation. So as we will see down below, they have developed the angular momentum equations and then they have combined all of these later on. So in the 3D theory we know that the angular momentum equation is nothing but sigma is equal to sigma transpose, but in case of shell this can be written as this g1 cross gi cross gj sigma ej, or that is also equal to gi cross sigma g superscript j. So this derivation also we have done over here, one can easily see. So this equation, when we expand out, some terms get cancelled out and other terms get combined in this format, and when we write the right hand side of this equation in terms of sigma transpose, what we get is this whole thing equal to 0. That means all these terms are individually 0. That means sigma is equal to sigma transpose. So both of these equations are identical, and when we take yet another form of this equation which are both same as described over here, you can see that when we expand this we get actually this. You can see we started from here and we are getting to here. So considering this one as the statement of balance of angular momentum, using g alpha is equal to a alpha plus zeta t comma alpha and g3 is equal to t, what we get is this. And in this form what we see are the expressions which we just derived of these n alpha, m tilde alpha and l. So please note that here m tilde alpha is appearing, not m alpha which was appearing in this momentum equation. So in from one of the places either we remove m alpha or we will remove m tilde alpha and write one in terms of other, otherwise it will be difficult to translate in or combine both of these equations. So we actually are going to remove m alpha and we'll be retaining m tilde alpha which is appearing over here. So this is the form of the angular moment balance of angular momentum, and this is the restriction which balance of angular momentum places on the admissible form of the constitutive equations. So now let us see how we are going to merge both of these equations, linear momentum and angular momentum conservation. So these are the steps which so next, first we take the left hand side term, the first term of equation 4.12b, which is this, okay, this term. So here only we have m alpha coming and we want to write this m alpha in terms of m tilde alpha, so we consider just this term, and we also see the expression of m alpha is given over here which we got already. M alpha is t cross m tilde alpha, so we have to write one more derivation, one more derivative of this m alpha comma alpha, m alpha comma alpha we have to write. So we take basically the derivative of this, so we'll get two terms, first derivative of t and then derivative of this term. So this is what is being done here. So first we take this term and write its derivative, so what we get is this t comma alpha cross m tilde alpha plus t cross this term m tilde alpha comma alpha. So this is just the product rule which is written over here, and now this term we can see is directly appearing in the angular momentum equation. You can see here. See, this term is directly coming here, so this can be replaced and written in terms of these two terms. So this is what we get from the angular momentum equation 4.15, and then if we proceed with the derivation steps, we get this form, and in some handwritten notes I will show you how to come from this to this. So we have this same LHS what we have over here. Okay, we start with this and we write this expression over here as it is. Okay, as it is written here in the first step, and then we substitute this from the angular momentum equation in terms of these two, and the third term is as it is, and then from equation 4.12b we write the expression of this. Okay, 4.12b, yeah, we have this term written in terms of the remaining three terms, and what we get is this. Okay, and this term gets cancelled out over here. Okay, and we get all the other terms like this, and we can see that this term is having t cross product something, and this is also having t cross product something. So both of these terms on the right hand side have something t cross product, and then on the left hand side we don't have t cross product, so we create that, and it is very easy to see that w dot t can be written as t cross t double dot. We have derivation steps for this also, and m bar can be written as t cross m bar tilde. This is some new quantity which is introduced, and this is the relationship which is given, and you can check the derivation steps and then we'll try to understand later on. So this is what the whole derivation of this. So everything becomes t cross something, and that something is collected in the brackets in the final form. So yeah, this is the final form. T cross all these quantities we get equal to 0 as the momentum balance, linear momentum balance, and combined with angular momentum balance. So here is the derivation of w dot is equal to t cross t double dot. So we know that from equation 3.21 that t dot can be written as w cross t, because t dot belongs to the tangent space of t, so it can be written as w cross t, and t dot is derivative of that, so it's product rule, and if we just expand it out and again rewriting t dot as w cross t, what we get is t double dot as this, t cross t double dot as w dot. So w dot was appearing in the equation over here, so w dot is replaced with t cross t double dot, and this m, which is applied load, director couple per unit length. In the previous page also we have, when we wrote equation 4.12b, we had this m bar dot t is equal to 0 and m alpha dot t is equal to, this is internal force and this is applied force, and both are actually perpendicular to t vector. So same thing is followed over here, and it's written that m bar tilde is also perpendicular to t, and basically m bar and m bar tilde are also now perpendicular to each other, and both are perpendicular to t. So it is also replaced over here, and this is the final form which we get of the final equation. So essentially this whole thing is along t, this whole thing is parallel to t vector, so we can write this whole thing as lambda t, and what we get finally is L bar, where L bar is L plus lambda bar t. So lambda bar is a newly introduced constant, and it is called as an undetermined director pressure, whose significance is analogous to the hydrostatic pressure in incompressible elasticity. So these are the two equations. Now we have completely eliminated m alpha and everything is now in terms of m tilde alpha. So these two equations have got both linear momentum conservation and angular momentum conservation. And also please note that this equation is a vector equation. We have not introduced any components so far. So this is the vector equation of force balance law for the shell theory. So we will stop here, and only one part is left out now. When we resolve these equation in terms of components, we have two options. One is the convected basis, another is the Cartesian basis or the director orthogonal frame. So when we resolve it along those frames, what happens, what form it takes, and then how we are going to combine it in the energy equation and the weak form development. So those things we are yet to see. Till then, bye bye, take care, and we will meet again soon in the next video.